Good morning, Dr. Piyush.
Yes, I can hear you. Can you hear
Yeah,
me? Afzal, yes, very good.
yeah. So shall we start?
Yeah, let's go. Yeah.
Okay. So good morning to all of you. Today we have Dr. Piyush Verma. First, I would like to introduce Dr. Piyush Verma leads the policy and regulatory innovation work at the International Energy Research Centre, Ireland, which is a funded body by the Irish government. He works on the intersection of technology, policy, and society, and has significant expertise on energy and climate policies, as well as policies around frontier technologies to accelerate the efforts towards sustainable energy efficiency. Governments of India, Vanuatu, and New Zealand on researching, developing, and implementing energy transition policies. He has also published several articles and opinion editorial pieces on energy and climate changes issues in the Irish national media, and has spoken in more than 23 countries on the need of transformational vision and disruptive leadership to bring innovations in policy formulation, coordination, and implementation. He has been selected as Global Future Energy Leader by the World Energy Council London in 2018. He also works as Vice Chair of the Energy Efficiency Expert Group at United Nations Economic Commission for Europe, based in Geneva, and as Regional Ambassador for Ireland in the Global Blockchain Business Council based in Washington, D.C. He has he is an electrical engineer with a postgraduate in power system and has a PhD in energy efficiency technology and policy from the University of Auckland, New Zealand. He has also completed a policy design and delivery program from Howard Kennedy School of Government, USA, and another program on 21st century policy challenges from University of Virginia, USA. So with these words, I would like to invite Dr. Piyush to please share your experiences with us. Dr. Piyush.
Thank you, Afzal, for the kind introduction. I hope you can hear me.
Yes, yes.
Yes. Okay. Thanks. So thanks for the kind introduction, and a pleasure to be here with all of you this morning. Not a very bright light, but apologies for that. And I think it's still 6 o'clock here in Ireland, and it's still very dark. Yeah, still winter has started, and it's raining, so cloudy here at the moment, and raining heavily outside. So yeah, there is
It's
not much.
6 o'clock in the morning.
Yeah, it's 6 o'clock here. So, but yeah, good morning from Ireland, and I hope you all are doing well. And this morning, I will present you around the microgrid from the policy perspective, and I'll take a couple of questions. Your burning questions from the what your research has been going on and what kind of challenges you are facing. So, happy to have some of the questions as well at the end. So let me share my screen first. Can you see the screen now? I hope you can see the screen now.
Yes,
So,
possible.
yeah, thanks. So yeah, this is a topic for today. As Afzal has already introduced, that I work in the policy area. From the policy perspectives of the not just from the electricity side or microgrid side, but from a broader policy perspective. So energy and climate policy, basically. So I work at the intersection of technology and policy and economics and society, so the social dimension as well. So that's my area of work. And because I'm coming from the technology background, so there is a lot of interest, around the technology-based policy and how technology-based policy can help the society, the social objectives, what we want to achieve in this 21st century. We are living in a complex world at the moment, and we have plenty of challenges, which is climate change is one of the biggest challenge of this century. So, and when we talk about climate change, it all comes to, because energy sector has the highest potential to tackle this unprecedented challenge. So, So, when we talk in the energy sector, there are different opportunities, new opportunities emerging, and how we can leverage on those opportunities to, make the energy sector. For example, in Europe, we want to target. In fact, we have announced a target. EU Commission has announced a target by 2050, a carbon neutral economy. So, if by 2050, if you want to become a carbon neutral economy, there is a huge role of the energy sector. So that kind of target I'm saying. And when we want to achieve this, so microgrid also is part of that. So I'll talk a bit about that in next couple of slides. So just a brief about the organization. So IERC stands for International Energy Research Center. It was established in 2012, and it's a funded body from the government of, Department of Energy, Government of Ireland. So we get most of the funding, core funding, research funding from the department, and then we also get, a funding. It's a competitive funding through the European Commission, and there are lots of private industry funding as well. So it's basically a kind of collaborative research. We are trying to bridge the gap between academia, industry, and government. So we are working on that intersection. And we have partners from 37 countries, 67 global partners. So it's a pretty much kind of international organization. And we have from a small consortium, from 2-3 partners to 18-20 partners consortium. So it's a pretty, from a smaller scale project to larger scale project we have. And all the research which we are doing, we are looking from the 5 kind of lenses. So one is, of course, technology. We are looking at like all kind of technologies coming into energy space, but we also look at from the data analytics perspective, which is a completely new area with the advanced digital tools and advanced data analytics, how those can help to maybe have better policy decisions, or maybe improve the technology performance, or maybe improve the existing business model, or maybe have a new innovative business model. So that kind of thing we are looking how data can help to make these kind of new opportunities. We also look at the behavior side. So from the citizen side, how we can change the behaviors and what are the current behavior patterns and what are the opportunities to improve on them. And then, as I mentioned, about the business models and policies and regulations. In my role, so I lead the policy and regulatory innovation team at IERC, and so we have got different technology teams, like 3 or 4 technology teams. There is one business model team, and so my team is looking at how we can. So we do a lot of research. We do a lot of academic research. We do a lot of kind of industry-oriented research, but there is a different kind of need for the policymakers. So policymakers are a group of maybe the people coming from the social science background, economics background, that kind of background. So when we are doing these kind of technology research, how that can be translated into an easy language for the policymakers, which they can understand. Because when we are putting our papers and those kind of things, into academic journals, it's pretty much a complex thing. We understand it, but why we do research? We do research to uplift the society. Ultimate aim. What is the ultimate aim? Ultimate aim is not about just publishing a paper. Ultimate aim is to improve the society. Have a better society. So if you want to do that, it has to be translated into somehow some guidelines, some targets, some policies, regulations. unless it is translated into some form of policies from the government, it doesn't make any, it may lie in the somewhere under scientific database, and you will have that kind of scientific impact, but it will not make the societal impact. So my team is looking at how we can tweak those scientific research, how we can translate into, according to policymakers' need, and provide them so that it can be translated into policies and regulations. So that's where I am sitting in IARC. Going into the core presentation, so I would like to highlight the when we are talking about the energy transition, it's a 4D at the moment, which is driving this energy transition agenda. And the 4D is decarbonization, decentralization, digitalization, and the last one is democratization. And because these 4Ds are very, very important, and it opens up, because you all are researchers here, it opens up completely new kind of, each area completely new dimensions, what kind of research is going on at the moment. So if you look at the decarbonization, for example, it's renewable is, of course, it's, we are talking about all this wind, solar, and biomass and that kind of things, and there is these are all giving you, how we can decarbonize the grid. But apart from this, how this electrification, it's electrification in a broader sense, like, you can have electricity at home, when we have electric grid, we can get electricity in our home. But what about electrification of transport system, for example, bringing the electric vehicles and developing the smart infrastructure to do that electric charging and bring those cars on the road. So ultimately it will be coming to the grid. So that kind of thing we are also looking, bringing not just your building electrification, but go toward the transport and maybe cooling system, or maybe cooking. So we are still, for example, in cooking, we most of us in India, we use LPG, so can we move, if it is coming, if grid is completely renewable, can we move towards that side? So that kind of electrification from a broader perspective. Of course, a smart grids, how you can make the connectivity between different stakeholders and different devices and equipments, and improve the overall kind of performance of the grid, operation, security, resilience, from all these perspectives. And efficiency, when we talk about renewable energy, come one step backward. Before renewable energy, we need to talk about efficiency, because if there is no focus on energy efficiency, you will keep building your generating stations, power generating stations. Maybe you'll bring solar and wind and that kind of thing, but from the economy point of view, it doesn't make sense, because the demand will keep rising, and you'll keep bringing the new power generating stations. So we have to focus first on energy efficiency to decarbonize the energy system. Energy efficiency is the first fuel, as mentioned by International Energy Agency. So because when you maintain the energy efficiency with these new technologies, if you try to improve the energy efficiency, there is, you can have a better capacity planning for the future generation. And I have highlighted here this decentralization, which I'll come in more detail in next couple of slides. But to highlight, this is about the microgrid. This is about what we are going to talk today, and in terms of not just about the microgrid, not just for your own generation, but also about the how, if you are generating your surplus energy, how you can sell it to others. How you can bring other participants into the system. So it's called P2P, which is you may know, it's called peer-to-peer energy exchange. And of course, when you're talking about these kind of decentralized system, the storage will come into picture, because sun will not always shine and wind will not always blow. So what will happen during those periods? So you need to bring the battery technologies in your premises to have that energy stored and use it when required. And then we are talking about the digitalization, and digitalization is all about the new technologies, digital technologies, it's about artificial intelligence or blockchain, or we are talking about big data, robotics, how we can leverage the potential of these to take the energy sector to the next level. Maybe in the sense of, so from digitalization point of view, how it can help. So for example, maybe you can have it's called a 4-stage, operation. So prediction, measurement, monitor, and improvement. So digitalization can help at each of these 4 stages. And for example, if you talk about prediction, can we predict the behavioral kind of consumers consumption pattern in a long term? So with these artificial intelligence and that kind of thing, you will have a better pattern, and because when we are talking about big data, it's big data will be coming into like maybe a volume of data, or maybe a variety of data, or so when you have these kind of huge amount of data, artificial intelligence can help finding patterns in those huge amount of data. It can do the analysis, it can find the pattern. So through these technologies, you can have better technology performance, better prediction of the consumption pattern, or maybe like we are talking about wind or solar. So you can have a better weather prediction, and because you can have a better weather prediction, with that you can have better planning and better demand and supply match and that kind of thing. So it can help all these 4 stages which I mentioned, and that's how we are trying to leverage in the energy sector. And again, democratization as the last D. And democratization is all about the bringing citizens at the forefront. Okay. So as I mentioned, we are doing everything for the society. So when we are doing everything for the society, still the society and citizens are not engaged enough in the energy space. So when we say energy, it's people think it's a very complex area, energy and electricity is mostly ingenious deal. But no, we need to change that mindset, and we need to activate citizens to make them active participants, into how they are, maybe they need to change their behavior, how they're consuming energy, and then how we can, make them, how we can empower them to generate and sell their own energy. So that kind of thing we are looking at from the democratization point of view. So when we are talking about, I'll go a bit deeper into microgrid side. When we are talking about microgrids, it's all about decentralization, as I mentioned and the earlier slide. So as of now, we had kind of centralized energy infrastructure, electricity market infrastructure, and that's coming from top to bottom. We have a generating station. It goes to transmission, it goes to distribution, and from distribution it goes to buildings, industry, businesses, transport, and everywhere, wherever it needs. So in that kind of system, you had a pretty kind of, there was not much flexibility. Okay. And you have, for example, you're getting electricity, you switch on, switch off your light, and you just pay for the bill. But now, when we are talking about the disruption which is happening in the energy market, in the electricity market, it's about kind of microgrids. So if you see here, each of these, the central dots, for example, each of these dots are like, for example, think about as a microgrid, and how each microgrid is communicating with each other. So this is here, different microgrids are communicating. If you see this example, there is a microgrid and there may be several households. So those households are maybe, they are generating surplus energy, they are sending to that microgrid, but from one microgrid to another microgrid, there is a communication, they may be selling and buying between these two. And then if you see this example, there are microgrids, and there are maybe several households, and they are just kind of, it's called, all the selling and buying of electricity is happening at that local level, and all the grid balancing and everything, it's happening at that level. So there is no connection with the other microgrid. So there are, what I mean to say here, there are, different kind of models are emerging. and it's unpredictable at the moment. It's uncertain which kind of model is going to work in the future. Which one will be creating or capture most of the market. So it's completely unknown at the moment. And it's a part of research. There is there is a whole lot of research going on about these different models, which I talk from the kind of how will it be only microgrid, or will it be a communication between microgrid, or will it be like peer-to-peer trading on a some kind of new platform, or like is that peer-to-peer energy trading is going to create a lot of technical power system problems. So these questions are still questions, and that needs to be solved. So will it be like grids or microgrids? And just to simplify that, the previous diagram, this is the microgrid, and you'll have coming from several sources, from wind, solar, battery, and like all these, maybe building is generating own, and there are maybe not just one-way communication, but maybe two-way communication is happening, and from one microgrid to other microgrid is going, and all these microgrids are connected. So the weather forecast, energy market. So it's not about just when we say energy market, in the existing centralized energy infrastructure, it's about the centralized energy market, and it's about at the pricing decision and everything happens at the central level. But now there'll be several local energy markets and several local energy producers. So there is another concept coming. You might have heard about the prosumer, and prosumer is about who is a producer plus consumer. So producer plus consumer will become prosumer, and that's a term which is emerging now when citizens wants to produce their own energy and want to sell into the market. So those prosumers, how they will interact into the system, what are and because there will be, when they will be coming to the market, so there are several kind of energy cooperatives and several new agencies and several kind of startups who are providing those kind of platforms for the local energy market. So for the microgrid, you need a different kind of, maybe softwares, maybe hardwares, and that kind of platform. So there are startups coming, so many new companies are coming to provide those platforms, or maybe, to operate your microgrid in your home, in your building, or in your premises. So there will be agencies who can operate those. So what I mean to say here is there are so many new stakeholders are coming into these, and looking at everybody's interest and incentives is really, really important when we are trying to have this kind of system. So what are the drivers and benefits? And when we look at the drivers and benefits, as I mentioned, active consumer participation is one of the key things, because if you want to make a reality, it's about bringing the citizens at the center. And when we want to think about bringing citizens at the center, just talking about energy, it's not going to help. Okay, it's not about just technicalities of energy, or maybe just from the environmental perspective, you say, okay, we want to reduce energy emissions. That's not going to help. And it's all come to boosting the local economy, creating local jobs and that kind of thing. So making the microgrid, bringing into communities and making it to reality, we need to talk in a different language. And we have done a lot of research, at the IESC on citizen side. So how we can make the citizens on the forefront of the energy transition. And all this is emerging that we need to talk about the strengthening local economy. Their awareness is about also still, maybe some of the citizens are coming at the forefront, but not, there are citizens who still, feel not much feel comfortable about the energy market, for example. So they think, how we can have that kind of, bring those skill sets into the local economy so that local people can get trained, local awareness about those policies, local awareness about those business models or revenue opportunities, how communities, they can invest, and when the revenue is generated locally, how they can get the benefit out of it, and that kind of thing. So of course, and then we talk about the, from the other dimension, the self-sufficiency at the local level, increased energy efficiency, because you are not going to, when you have a microgrid, you are not going to, a distribution for a, transmission and distribution, you are not going to use much of the poles and much of the wires, and that kind of thing. So there'll be losses and all will be reduced. So from energy efficiency point of view, there is a huge benefit from that side as well. And of course, grid reliability, because there may be less complexity in terms of how many consumers are connected, and that can help to improve the whole reliability and security of the system, and improve social cohesion. Social cohesion, it means, so if you talk from if a microgrid is owned by a community, how that community, being a part of that, because they'll be operating that microgrid, so it will bring a kind of social cohesion. Social cohesion, it means if they are investing in the making that microgrid, so they'll feel a part of a community in terms of connectedness, in terms of solidarity, and when they'll feel that it's all coming, the local investment is coming at the local level for the local people, by the local people. So it will improve the overall trust in the society, and trust in the system, the democratic system and the government system, so that, okay, government is also providing these kind of, empowering the citizens and stakeholders to have this kind of platform where citizens can participate. So the overall kind of the social growth will happen through these platforms. And why they are crucial now? So this is a slide I really wanted to show here, because if you see, just think of yourself, you live in a home, you consume energy, and if you look at the most of us, do at the moment, it's about just the question of getting the light. Okay, when I'm switching on, am I getting the light, or is my fan running, or is my AC running? Okay, and maybe if you go to next stage, we check are we getting 220 volt? Okay, most of us in India, if you go into rural area, maybe we are using stabilizers and that kind of thing. But it's about a lot of performance-based thinking we had, the traditional customer. It's about the reliability, whether it is safe, the pricing should be affordable, and then kind of, do I have information, how much electricity I'm consuming and that kind of thing. And then if I have kind of blackouts, if my transformer is burnt, is my problem getting resolved, and how long it takes. So that kind of performance-based system and the traditional system we were looking for, as a consumer. But now when we are moving towards this new energy system, the new energy market, where citizens want to engage, so it's a lot about the the interactivity with the system. Maybe few of us have installed solar panel in India, if you see, and they have installed battery storage technologies, and they are monitoring their pattern, like how much solar energy they are generating every day, so they are monitoring the data. They are also thinking of how I can sell my energy, so they want to collaborate with other local utility. So all this is coming into engagement based mindset into picture now with this new energy system, and we need to leverage that, the collaboration. We need to leverage on the kind of convenience. For example, you can run your AC from your remote, okay, and that's the power of digital. So if you can run your AC with your remote, with your mobile phone, remotely, you don't need to be in the room. So how that kind of convenience can help, not just to make your life convenient, but also improve the overall performance of the system. So we need to work on these, leveraging those technologies to to have kind of improved operations and improved comfort and improved improve the energy and emissions performance. And also, the in terms of choices in the sense like, for example, do you have in the market when you are engaging as a local microgrid, do you have choices where to sell your energy? So where to sell your energy means finding where you can get the best price, okay? Because it should be a competitive market, and wherever you will get the best price, you will sell your electricity. So that kind of choices are also coming into picture. And this is a picture. If you see, from the I talked a lot about from the citizens dimension and why it's really important to bring them at the forefront. So, and there are still citizens and consumers who don't keen enough to engage. So what are the challenges we are facing from energy consumer to become an active energy citizens? So why, where, and how? So we did this research and we found that the three key problem is citizens, they don't know where to engage. They are lacking that kind of motivation. They don't know what is the platform and where I can go and that kind of thing. So if we can solve these three problems, and it looks like a simple question, but if you think from a research point of view, it goes so deep, all these three questions. And so many data sets are involved in solving these questions. But we need to solve if we need to bring that kind of decentralization to be part of the existing centralized infrastructure, and if we want to achieve that overall objective. So I'll elaborate a bit on this why, how, and where. So if you look at the citizen engagement complexities, it's about there is kind of lack of willingness, for example. So how you can solve that lack of willingness? Each of all these is a research question, okay? And for example, communication gap, lack of transparency in the system. So transparency, for example, maybe there are policies, microgrid policies, but microgrid policies are not being transparent and there is not much awareness about it. So because there is no transparency and there is no awareness, people are lacking in terms of their motivation, because they don't know what kind of motivation I'm going to get, because everybody looks for their own incentive and interest. So if my incentive and interest is not aligned with the bigger objective, how I'm going to be part of that? And all this, when there is lack of transparency and lack of awareness, it creates lack of public trust. And because microgrid is still an emerging technology, there are no structure of engagement, like how that can be, what is the model where you can bring maybe 10 houses in a community, bring them together. If they are able to invest in a local microgrid, they will invest enough, okay, in that system and have a local microgrid. It will go to those homes, and then it will also create local jobs. It will also, the local supply, whole local supply chain to bring into the system. But how all this is going to happen? So there is no kind of platform, a structured platform or a structured engagement mechanism where citizens and societies can come forward and, have a debate on that and have a, develop an understanding how we can become an active participant. Local government also, local government comes into picture, but they are not empowered enough from the energy side. So all these local authorities, if you see local municipal councils, there is not much focus on energy. They have been doing roads, lights, and that kind of thing. But if we want decentralization of the energy transition, if you want to, as a country, if you want to achieve that targets, that the kind of ownership has to come down, and that ownership has to come down at the local authority level. We have to set local targets, not just national targets, but breaking down the national targets into local level, local cities, local municipal, all and that targets will bring the ownership to local authorities, and that local authorities will get engaged with local stakeholders to build the supply chain, to bring the microgrids in their own area, and to bring the citizens as part of that solution. So that kind of things need to happen. And of course, the technical jargon and social benefits and these kind of things, as I mentioned in my previous slide, we need to highlight these kind of not just energy and emission benefit, but talk about the local economy as well. So yeah, coming from the regulatory and policy perspective, it's not about just reacting to a market, okay? So just looking at the market and what's happening and just react immediately, but we need to think from how we can create a market from the for the microgrid. And if you want to create a market, we need to be proactive. And so I've highlighted some of the key bullet points here, like for example, key terminologies. I'm not sure if prosumer, the word prosumer is defined in different states or at the national level in India at the moment, but we are using a lot of like key terminologies in the European regulation and in the Irish regulation. These are now being defined by policy makers. What is active energy citizen? Who is energy citizen? Who is prosumer? So these kind of new definitions need to emerge, need to come into guidelines, need to come into policies. You need to bring the financial incentives for the microgrid, for the communities to participate in. And that financial incentives could be some kind of tax rebate. If you're going to pay, purchase solar panel, there should be no tax and that kind of thing, or maybe some kind of, a direct grant, or maybe zero interest loan. Maybe I'm really keen enough to bring solar panel and battery technology in my home, but I'm not able to afford the initial cost. So is there any zero interest loan is available, which I can take from the bank and, get it installed and pay in the long term? So that kind of thing also need to be, bring in from the policy perspective. A new tariff structure in terms of all those we are talking about feed-in tariff and that kind of things. So that need to be also redefined from the microgrid perspective, so that microgrid can, the people who are having the microgrid, how they can, leverage the benefit of these new tariff, or maybe if they want to sell into the grid, not just the local house in the other community, but if they want to sell into the grid, so what kind of tariff structure is defined, for that. So that will, selling and buying both will come into picture. Enabling the integration, it's like you need to have a centralized system, but you also need to have a decentralized system. So merging, integration need to happen, but that integration is not easy. So we are like, you all are working from the control system and, power system and that perspective. So you all know that how these voltage stability, power quality, and the frequency stability, all these technical issues come into picture. So this is, integration is not easy, and that's the biggest challenge which we need to tackle at the moment. We need to empower utilities, with new guidelines and policies. We need to have that, as I mentioned, targets and mandates we need to have at the local level, not just at the central level, but we need to bring it down. We need to have that simplicity in terms of consumer mindset, not just because a lot of policy language. So that is also very complex. So we do a lot of technical research, as I mentioned earlier, that is complex. We need to simplify it for policymakers. But from policymakers, if you want to take the policies at the local level, you need to make it more simplified, and you need to make it more interesting for the common people. Until unless they understand the policies, it's not going to help to achieve the objective. And we can only achieve objective if it can become, a kind of, we can give power to people. So we need to think from that perspective, the simplification from technology to policy to the people. And collaboration between all actors and future roles. As I talked about, new stakeholders are coming into the picture. So new stakeholders need to be, their roles and responsibilities need to be defined, and there should be some kind of cohesion, the collaboration, not much competition, but that very strong collaboration need to happen to achieve the broader objectives. And it will bring overall energy security and reliability and everything. Technologies, a lot of technologies we are creating, but from the technologies, it also need to go to the commercialization stage, which is really, really important, from the microgrid perspective. And that commercialization, then the next stage, we need to develop the business model. What kind of business model to help, to create a local energy market. So we need to think from all those three dimensions: have the technology, bring it to commercialization, develop the business model, and bring into, the policies and guidelines and regulations. So this is, I just wanted to highlight from the microgrid, what are the current barriers we are facing. And you might be, most of you might be walking into technical dimension, like grid integration and all these areas, but there are a lot of other challenges. And the other challenges is, like, if you see economic barriers, for example, there is economic barrier in terms of site choice, which is very important when you're going to have a microgrid. Okay, site choice or external benefits and cost, or as I mentioned about the upfront cost. So we need to, what I want to say here, we need to bring in kind of interdisciplinary thinking, a system thinking. So in system thinking, what you do, you not just think in your own perspective, but you bring others' perspective as well to find the best solution. And that needs to happen because it's all integrated. It's not just the technical problem. You can solve the technical problem, but you need to collaborate with the economics. You need to collaborate with the market specialist. You need to collaborate with the policy specialist to see those challenges and whether you can contribute anything from your side, from the technology side, to meet the challenges of economy. So, for example, if the upfront cost is very high, can you develop a technology, affordable technology, bring some innovation, or maybe do some new kind of invention, completely new invention. So that kind of thing need to happen. So this bubble, as you can see, it's going into each other. So that means, it's a system thinking need to happen, not just work in silos to solve all these challenges. And I will encourage you, if you're doing this research from the technology side, go beyond your comfort zone. And go beyond your comfort zone, I mean, think about not just technology analysis, but maybe do one research on techno-economic analysis. Okay, maybe do one techno-socio-economic analysis. Okay, maybe do one research on not just on the technology, but bring the technology and bring the citizens, and work out, do the research on that intersection and see what are the complexities citizens are facing when we are talking about that technology. Look at the, not just technology, but look at the infrastructure, whole infrastructure, So develop a mind map, for example, mind map in the sense, before going into research, come back one stage and ask what are the critical questions from an infrastructure point of view. So we are going to build microgrid in one of the rural area, for example, in rural India. And so looking at the infrastructure, do we have capacity at the local level? If not, how we can bring those capacity at the local, the people, the technical expertise at the local level, to maybe stay there for a long time and, develop the microgrid, operate the microgrid and that kind of thing. I'll give you one example here. It's coming into, in my mind at the moment. I lived in Vanuatu, a Pacific island country, for some time. And Vanuatu is a highly underdeveloped country, and it's highly sensitive country in terms of climate change. And there are a lot of focus towards energy as well, because it's a climate sensitive country. But because it's underdeveloped, and most of the country is running on diesel, so because it's running on diesel, so you can think about the emissions, performance, and everything. So they want to switch into renewables. But the problem is, it's on a small island, a small number of people living there. And the people from outside, the experts who need to develop that microgrid, nobody wants to go. Nobody wants to develop it kind of, because when you go there, you suffer with a lot of other things, So when you suffer, how you can think about bringing those, expertise to that island to develop the facility, to operate the facility. So these are the key questions, when you think from the system thinking, this will come into picture. So I would encourage to go beyond technology in your research. And I just wanted to highlight here, the last few slides. It's about when we are talking about microgrids, it's immediately coming into the P2P energy model, peer-to-peer energy trading, and we are talking about with blockchain and blockchain technology. The blockchain technology has got so many other applications, but you will not believe, energy sector is the second highest application of blockchain technology, after finance. So in the energy space, there are so many new applications, from grid operation and at the centralized level to local energy trading. Everything is being explored, from renewable energy financing to a smart charging infrastructure. Everything is being explored on a blockchain platform. And just look at how many companies are operating. 189 companies are operating at the moment. There are a number of projects are operating, and $466 million is already invested to look at blockchain in the electricity market. So this is also a completely new area to look into, how blockchain can help make the microgrid a reality, or make the kind of peer-to-peer energy trading a reality. How we can improve the trust, transparency, collaboration, and that kind of thing. So the blockchain technology has a lot of power, but in terms of asking, we need to really ask the right question. Maybe you can solve some of the problem with simple piece of software. If you can solve with simple piece of software, you don't need to go for blockchain. Why you are going for complex technology? But blockchain has certain features, which you can leverage to solve your challenges. But it's about asking the right question, I would say. So we need to think from that perspective. And these are the two projects which I wanted to highlight here. So I was a project manager for this. When I moved here in Ireland in 2018, I was given this project as a project manager it was the first Ireland's peer-to-peer energy trading project. And it was a one-year project funded by the Irish government to look at, just to explore how this blockchain platform for peer-to-peer energy trading is going to help. So, it was a consortium with 7-8 different partners. We had some academic partners, we had some industry partners, and we brought kind of different experts in the sense, hardware expert, software expert, the energy market expert, and they all work together to find out, how this developing kind of, for example, different kind of trading algorithms. Okay, so what kind of trading algorithm can be most efficient if you want to do peer-to-peer energy trading, or what kind of hardware requirement is, or what kind of software requirement is, or what kind of in the future, if you're talking about microgrids or peer-to-peer energy trading, what could be the market size and forecast? What are the current challenges in terms of policies and regulations? And it also comes a lot on the standardization side. For the microgrids, we might new new technologies and new devices. So do we have standards for that? So looking at those as well. So we look at the when the from the system thinking point of view, as I mentioned, and we highlighted all the key stuff. So there are papers already published on this. The project name is Innerport. If you want to have a look, you can have a look at the Innerport. And there is one paper on this, but there are a couple of other papers are also published on the energy trading algorithm and the policies and regulation and that kind of area. So, but from this research, it gave us a lot of learning, and we moved to another research, which is called Cooperative Energy Trading Project. And that's also a blockchain-based peer-to-peer energy trading project, which is a €3 million project and funded by the Irish government. And this project is looking at, how you can, so it's called SENSE. The project name is SENSE, Cooperative Energy Trading System. And this project is trying to build a platform to bridge the gap between, prosumers, community grid, wind farms, solar farms on the one side, you can see. So all these, it's called like community-owned solar farm or community-owned wind farm. So these are all kind of microgrids, okay? And on the other hand side, there might be consumers and, the distribution system operator, for example, okay? So on local utility companies, so how you can bridge the gap between, these two through a central platform. And that central platform will be a kind of energy cooperative agency, and that energy cooperative agency will look after, if you want to sell your electricity, or if you want to buy a renewable electricity from a local microgrid. So it can look into all those aspects, and there might be, so we are trying to have develop the mechanism, how it will work. And it might be, there might be some maybe service charge kind of thing. And with that service charge, this cooperative agency can help to sell your electricity and at the best price in the market. So you just tell your cooperative agency, local cooperative agency, that okay, I have this much of surplus energy and I want to sell at the best price. They'll take the service charge, and they will they'll take the responsibility for selling your electricity. And similarly, if you want to buy, you can tell, okay, no, I don't want to be connected with the centralized grid infrastructure, but I want to connect with a local microgrid. I want to get my electricity with renewables. How I can get it? Being a responsible citizen, because you don't want to consume just coal, oil, and gas-based electricity, because you have a local microgrid, and local microgrid is already generating energy, electricity from the solar and wind and other renewable energy. So being a responsible citizen, you want to take from the local microgrid. So how you can be participant in that, and how you can leverage that. So that kind of platform we are trying to develop with this other project. And that's all. That's all from me. And I would say, yeah, two things. When you think about the microgrid, bring the citizens at the forefront. Okay, we are, because in India, I see a difference between when we talk about these kind of microgrids and these concepts here in EU, and when I see in India. So we talk about microgrid from the energy access point of view. Okay, when a rural community doesn't have electricity, we talk about microgrid. Okay, bring the microgrid and provide the electricity. But it's not just for them. It's go into broader space. And think about the broader local energy market. And think about the, bringing the citizens to be part of that. Think about the social cohesion and social capital in terms of social trust, and social trust in the policies. And from policies, capacity building to local jobs. We are talking in India, Atmanirbhar Bharat, self-reliance India at the moment. So this is an opportunity. This is not just an opportunity to provide where there is no electricity, but you can go beyond that. You can create local jobs. You can the local people can get trained. And when local people get trained, their thought process will increase, their thinking will increase. They'll have a better life. And when they'll have a better life, the whole society will improve. Because everything starts from the root cause. So from the root level. So if you work at the root level, the chain will keep going, and that's how we can have a better society. And then from the other side, I would say, from your research, when you are doing your research, not just think about the technology. Okay, go beyond your comfort zone. Do your technology research, but technology is not just the only challenge. There are it's a very complex puzzle, and there are so many pieces into that. So you have to bring all the pieces in the right way at the right time, in the right place to make the system work. And that's how you need to look into other areas as well. Do your technology research, but look at the technology work which you have done. Is it really economically viable? Is it really worth for the society? Can society afford it? So that kind of question you need to ask yourself, in your community, in the sense, I mean, in your academic community, in your discussion. And that will help, achieve our national objectives in terms of energy and climate change. So with that, thanks very much, and I'm happy to have any question.
Thank you so much. We have a question about from could be same kind of system solar trees.
Sorry, cannot hear, Abjal.
Yeah, there is a question in the chat box.
In the chat box.
Could this same kind of system be developed with the solar trees in a coastal?
Sorry, solar tree? I cannot, I think.
Solar trees in a coastal belt.
Okay, yeah. So yeah, any type of solar technology, it's I think that is also part of research. So it's not a very well established area. Okay, and as a researcher, we have our responsibility to make it more established. Okay, like for example, you are talking about solar tree. There could be another area we are talking about floating solar. Okay, like the floating solar panels. So these are all new emerging area, and it's again, it could be technology, could be worse, but I would say look at the technology, society, economy. So we need to look at economic viability as well. So technology is good, but is it from the cost benefit analysis point of view? Because when you look from the policymaker's perspective, it comes to cost benefit analysis, and the technology may be very good, but from the cost benefit analysis, if technology is not affordable, not giving that kind of benefit what we want to achieve, I think it needs more research. So I would say, yeah, it's still part of research. It's possible, but we need to I think engage more on that.
Okay. As you have, I have one query. As you have handled, so many projects related to this, energy market and peer-to-peer energy. So, do you have any idea about that? What are the, still possibilities are there that we can explore in this peer-to-peer energy marketing?
You mean in terms of research area?
Yeah, exactly, in terms of research area.
Yeah. So in terms of, as I mentioned in my presentation, it's a new research area, okay, a peer-to-peer energy trading. And I think it's the next stage of the microgrid. We are talking about the microgrid, but microgrid could be, it could be maybe just in a community, but maybe a building could also have own solar panel and maybe generate their own electricity. That is also a microgrid. Or maybe a company, for example, a steel plant could have own, energy generation, and that will also be a microgrid. But the next stage research is coming into peer-to-peer energy trading, okay? And I think that peer-to-peer energy trading is as I showed in my presentation, there are so many new models emerging, and still it's very, very early part of research. So I think we need more research in that area, and not just from the technology dimension. We need to look from the policy dimension as well. We need to look from the business dimension, kind of business model dimension as well. And as I said, it's of course we are working. I'm mentioning so many times, but I'm mentioning it so many times because it is really important. Because when we are working from the policy perspective, you don't need to just work from the technology perspective. Do your technology research, but broaden your thinking. Okay, broaden your thinking, and go look for like technology affordability, technologies, social dimension, behavior of people, how citizens are responding. Maybe you have developed something, how, get the citizen response on that, common people. If we have done some research, if you are not able to make in a simplified language which simple people can understand, then research is not worth. I would say we are doing the research for the society, and go into the next stage. Bring it into, translate into language which policymakers can understand, translate into language which citizens can understand. And if you are able to explain your research to a layman person, to a common citizen, okay, and ask those questions, the question from those people, or maybe let them ask question on your research, and then see where your research can go. And I bet you it will make real impact on the society. So that's how we need to work. But this is all new research area, and we need to engage more.
Okay, so we have another question that could we apply the blockchain technology for the smart grids as on today?
So I think there are more than 100 demonstration projects, and most of the demonstration projects which have happened all over if you see from Australia has done, Singapore, in Ireland we did, in Netherlands, so many countries have done this project, okay, and so many companies have gone, from demonstration to the next level of kind of the demonstration. I would say they are trying to scale the technology to the next level, and it's working at the moment. But at the same time, there are other companies who are they are not using blockchain technology. There is a company in New Zealand. They are doing the same kind of peer-to-peer energy trading, but they are saying, okay, we don't need blockchain technology. We can do the same trading with a simple piece of software.
Okay.
So it's about, it's about kind of do the blockchain research as well, but look into alternate possibilities as well, and see like, okay, is that really blockchain is really worth having, or is it the same problem we could solve with, the existing software? One kind of, one of the electricity market expert asked a question one day, because I'm a blockchain enthusiast, and I made so much presentation on blockchain. So the question was like, we have been doing the trading, the same kind of trading at the centralized level. If you see in the central electricity market, the same trading was happening since hundreds of years, electricity trading. And if we can do the trading at that bigger level, why can't we do the same trading at the community level between two microgrids? Okay, and when we are doing the central grid, it was there is no blockchain. So why we are talking about blockchain at the local level? Can't we just use the same software which we are using at the central energy trading, bring it down, scale it down, and use it at the at the local level? So that kind of question could be asked, and as a researcher, you need to justify. So yeah, I would leave this, with you need to think like, do we really need blockchain, or do we need some other algorithms?
Okay. Thank you, Piyush. We have another question: how to ensure the energy security and reliability in rural India? Do you have any idea?
Yeah, so in terms of my, microgrid is the best answer. In rural India, we are still struggling. And I'm telling you about my home, where my parents live in India. They never get to 20 volt. It's still 150, 180, and they struggle. We have a stabilizer in our home, so and I think that kind of thing. So not just one solution, microgrid, but microgrid is the solution, but we need to look at other aspects as well, go at the root cause, finding why that is happening. And if you go at the root cause, so many things comes into picture, from power theft to poor infrastructure. So we need to have that kind of research as well, how we can reduce the power theft, or maybe how we can improve the infrastructure. Because of poor infrastructure, the required the supply level is lacking, and because the supply level is lacking, there are so many other sufferings, which people have to go with that. So it's not just one solution, a combination of solutions we need to look, and then only we can solve all those reliability, security, and stability, and those kind of problems in rural India.
So there is one more question from Mr. Abhijit Bhagat. He is asking what's your view on PM new initiative of one sun, one grid?
Yeah. So in India, yeah, I heard about that. I think one nation, one grid is also coming, and one world, one grid is also a kind of new thinking coming. How we can connect the all over the world, one world, one grid. And this is all fantastic. This is possible because of the innovation which is happening. The innovation I talked about, digital innovation, the kind of technologies from artificial intelligence to big data and all those advanced analytics which we have, that will be possible. And that will be fantastic to have. But in the future, when we want to empower citizens, at the local level, that's also going to decentralization going to happen. You cannot just have the centralized infrastructure. From reliability and security point of view, that's having that one nation, one grid, one world, one grid it's really, really important, because the kind of uncertainty we are going to face, the uncertainty in terms of, because of climate change. Okay, so because of climate change, what's happening? Unpredictable weather pattern. When we will get flood, and when we will get dry, or when we will get earthquake, and that kind of all those things coming. So because of that, there is a lot of uncertainty in the future. Right? If you see the models, there are unpredictable models in terms of solar patterns, or wind patterns, or wind velocity, and that kind of thing. So when we have that kind of uncertainty, I think from reliability and security point of view, that's really important, having a connected grid, so that if in one area we are not getting electricity, we can immediately connect with the other grid and we can get the electricity. So that will be one part of it. But at the same time, this part is also going to be merged, because if we want to decentralize the electricity, decarbonize the electricity system with the renewables, bring the renewables and achieve our climate change objective. So we also need to do the decentralization, bring the microgrids. So I would say go from top to bottom, and top to bottom means in the centralized electricity system, go to one grid, one nation, and in the grid, keep integrating renewables, but you need to go from bottom to top as well. Bottom to top, bring renewables in the local areas, and in that way we can meet the target somewhere in between in a much faster way, rather than just coming from the top to bottom. So we want to become, by 2050, if we want to become a climate neutral world, we cannot just coming from top to bottom and we can achieve that. We need to take the bottom to a top approach as well. Okay, because there is a scarcity of time, so we need to think from multiple dimensions as well.
So we need to work in the same way on mini-grid and nano-grid also?
In terms of nanogrid, it's still I would say very, very early stage, and I'm not sure if maybe, because if you think microgrid is still not established, and nanogrid might be later stage, but it is still too far, I would say. I think microgrid still needs a lot of research to make it stable and to make it integrated with the existing system. Because that's the biggest challenge we are facing at the moment, integrating into existing system. And integrating into existing system means the centralized system. There are a lot of these, as I mentioned, voltage, frequency, and power quality, and all these things we need to solve. So the nano grid will come much later, I would say. Of course, we are doing research, so we need to be forefront. And I'm not aware of nano grid research in Ireland at the moment, as far as as far as I know. There's no nano grid research, but there is still a lot of research going on in the microgrid area. So it will come, but maybe after certain years.
Okay, sir. So there's one more question from Mr. R.S. Kiran. Any work related to the 3D printing and rapid prototyping is being introduced into the research?
3D printing and this new area of research, I saw a few examples, and I just 2 days back, I was making a presentation in the UN, and we have written a report on digitalization of the energy system. And as I'm the vice chair of the Energy Digitalization Task Force in the UN Economic Commission for Europe. And being a vice chair, my responsibility is on the look after the energy sector digitalization. And when we are looking at energy sector digitalization, we have published a report on that. It's a brief report. And in that report, we looked into all these AI possibilities and 3D and all. So if I remember correctly, there are some examples, from the 3D printing is also given, highlighted by some of the other experts. They were working with me on that project. But yeah, of course, there are 3D printing possibilities as well in the energy space. I don't remember any concrete example, but there are.
Thank you, sir.
Hello, sir. Sir, good morning, sir.
Good morning.
Sir, I have it, sir.
Sorry, can't hear you, Ramesh.
Sir, I have a. Hello.
Yes.
Hello, sir.
Yes, tell me.
Community participation, actually. Sir, how we mold this community participation in microgrid in mathematically, sir?
Okay, community microgrid, how they can participate?
Hello, sir.
Sorry?
Sir, community participation is okay, sir.
Yeah.
How we mold community participation in terms of mathematics means
in terms of
in the microgrid, sir.
Yeah. So in terms of when you're talking about the modeling, what is model? So model is basically a kind of if you think from not from a complex point of view, model is just kind of you are analyzing some data, and based on that data you are developing some scenarios, and scenarios in terms of, okay, if I will do this, what will happen? Okay, if I do this, what will happen? So that's the model. Okay, so model is not just always in terms of MATLAB. Model could be in terms of your thinking as well. So in terms of thinking, when you are developing a model, think about a particular behavior of a citizen, of a community, which can help activate the local energy market, or think about a policy from the policymaker which can boost the local energy market, bringing more microgrids. So modeling could be in a simple thinking as well, not just in terms of MATLAB, but it's kind of behavioral modeling. So there, for behavioral modeling, for example, there could be another piece of software which you can do that. But I'm saying, just think about simple things. Like what kind of policies we need to bring. And if you bring maybe zero interest loan Okay, so if with that zero interest loan,
Sir.
think about how many, like, citizens from a particular community can be can be an active participant, or maybe they want to kind of contribute into the local microgrid from their own fund to become a kind of cooperative, the community microgrid. And when the community microgrid we have, the money which they have invested to build, it will go into the into their pocket. So it's kind of creating the local infrastructure. So that kind of modeling can happen in thinking as well, not just with this piece of software. But piece of software could be not just in the technology side. The piece of software could be economic modeling software. Okay, the piece of software could be behavioral modeling software. So in different areas, there are different kind of modeling softwares. Okay.
Thank you. Thank you very much.
Thanks.
Yes, any question from other participants?
So there is one more question from Nahid. It is, what is DSO, ESBN in cooperative energy trading system?
Oh, it was on the slide. Yeah. Okay. So DSO is distribution system operator, and so it's an Ireland slide. So I put that directly. So DSO is distribution system operator, and ESBN is the company, ESB network. So ESB network, our company here, is the distribution system operator who distribute the supply. But it could be like in India, for example, there could be other DSOs, but it means distribution system operator.
Any other participant? I think all the questions we have covered from the chat box also. If still any participant is interested, then please ask your query. Or I think we should conclude. So thank you, Dr. Piyush. It was a really very wonderful talk, and as far as your peer-to-peer communication is concerned, or your energy research project is concerned, yes, definitely it is very important to get into the details of your other socio-economic aspects also. And I hope the participants will be benefited, and if it is required, then definitely we'll get back to you for any kind of research collaboration or research funding. I hope it will be fruitful. So with these words, thank you so much, and thank you for sparing your valuable time from your busy schedule. I know that you are a very busy person, so it's really very thankful. I'm really very thankful to you that you have spared some time. Since 6 o'clock in the morning, it is very difficult to be ready and then start your presentation. So thank you. Thanks again.
No, thanks very much to all of you, and thanks to the organizing committee, all the participants, and it was a pleasure to be with you this morning. Happy to, I hope you have got some insights, and it could help your next stage research. So good luck with that. Thanks very much.
Okay, thank you. Thank you all the participants. Feedback link has already been shared. You are also requested.
Thank you, Dr. Piyush.
Thank you, Nafish sir. Kya hal chal hai?
I'm very fine.
good.
How are you?
Glad
Good to see you after a long time. Yeah, same here.
After a long time, after 10, 12, 13 years, I don't know how long.
Yeah, exactly. I was looking for, I was even looking on your face only. Really, it's very good to see you after a long time.
Yeah, it's a long time.
I think it is 2007 or 2008 we must be there.
Yeah.
Yes, it has been very long. Yeah.
Yes, now Dr. Nafis is working as HOD of Electrical Department, DIT University.
Oh, very good. Yeah, we have lost touch since then. when I moved, but it's glad to see you here.
Yeah, really. Me too. Same here, sir.
Yeah. Okay, all right. Thanks very much.
Okay.
Thanks
Okay
to all
then.
of you.
Bye.
Bye.
Thank you.
Thanks to
Okay.
all.
Bye.
Hello. Yes, but sir,
Yeah, I'm here.
shall, shall we start, sir?
Yes, yes, we can start.
Okay. Yes, Dheeraj, please proceed. Yes, Dheeraj. Dheeraj, is it audible?
Yes, sir. It is audible.
Dheeraj.
Sir, looks like you are audible to us, but not to Mr. Dheeraj.
Okay, let me check.
So there is some network issue at Ajay Dheeraj's end, na? So he'll be rejoining shortly.
हाँ ठीक है सुन लिया मेरे को वही नेक्स्ट तो बताऊँ ठीक है ठीक है ठीक है Yes, Ajay, Dheeraj, is it audible?
Hello, is my voice clear?
Yes, Ajay, please start.
Yeah. So sorry, there was some problem in the net. So good afternoon, one and all present here in this short-term online course that we are conducting here. Well, myself Ajay Dheeraj, one of the member of the organizing team, and I would like to heartily welcome our guest of honor, Dr. Abdul Hamid Bhatt, and all the participants. So first, let me give a brief bio of dear sir. Dr. A.H. Bhatt is currently working as head of the Electrical Engineering Department in National Institute of Technology, Srinagar. His research area includes power electronics, electric drives, power quality, improved power quality converters, custom power devices, active power filters, multi-level converters, AC-AC converters, matrix converters, DSP application to power converters, flexible AC transmission system, that is FACTS, AC and DC microgrids, smart grid, and few more. So let us all listen to him and learn the tips and tricks on the topic modeling and simulation of microgrid. So once again, I would like to welcome dear sir, and I would ask him to present his PPT.
Thank you, Mr. Dheeraj.
Yes, sir.
Yeah, the screen visible.
Visible, sir.
Uh, Good afternoon to all of you, all participants. And first of all, I would like to thank the organizing committee of this online short-term course for giving me an opportunity to speak about a topic of which is a topic which is related directly or indirectly related to the short-term course. This online short-term course, as I can see, it's on stability analysis, protection, and control of microgrid, and that is SPCMG 2020. And my topic of discussion will be role of isolated bidirectional dual active bridge, that is DAB converter in DC microgrid. Actually, I directly don't have any work in AC or DC microgrids, but I have one of the PhD research scholars who has done some work on DC microgrids, and he has used isolated bidirectional DAB, that is dual active bridge converter, for power control and for other purposes in a DC microgrid. He has already submitted the thesis, and we are waiting for his examiner reviews. So based on his research area under my guidance, I have chosen this topic as it is directly related to your short-term course title on microgrids. So I would again like to read my topic of discussion, which is role of isolated bidirectional dual active bridge, that is DAB converter in DC microgrid. These are the contents that I will be presenting briefly. My presentation will not be very lengthy. It will be a brief presentation. I will introduce, first of all, microgrids, AC microgrid and DC microgrid. I'm pretty sure that many subject experts have already done this job, but I will try to introduce these topics from the point of view of application of these dual active bridge converters in microgrids. Then some of the control methods for control of this dual active bridge converter in DC microgrid, I'll be discussing briefly. Some simulation results which my research scholar has developed during his research study, and some experimental results I will be sharing with you. Now, this is the block diagram or schematic diagram of AC microgrid. I'm pretty sure, again, that you are already acquainted with this. Many of the subject experts might have already introduced these AC and DC microgrids. As you can see, we have a distribution network, then we have a step-down transformer. This is high voltage AC bus, this is low voltage AC bus. And then, we have from here wind generation, we have solar generation. The wind generation is supported by AC to AC converter. The solar cells or solar panels are supported by DC to AC converter. And then this is our AC bus. And then we have AC to DC converter, and this is our battery energy storage, and we have AC loads. I don't have much to talk about it because I am sure that you already know about it. This is the DC microgrid, which will be my topic of discussion with you. Now, in this DC microgrid, you can see we have renewable energy generation. I have shown only solar cells. There can be wind generation also. There can be other types of renewable energy generations. I have, just for simplicity, I have just taken one source of solar, this renewable energy generation, that is solar panels or solar cells. And then we have a DC to DC converter, and this gives rise to a high voltage DC bus. Actually, this is a boost converter, boosts the voltage, and it creates a high voltage DC bus. And then on the other side, you can see we have a low voltage DC bus, and this low voltage DC bus, we have a battery energy storage system. We could have supercapacitors also. We could have other types of storages also. I have, for simplicity, shown only battery energy storage there. Now, between these two buses, that is between high voltage DC bus and low voltage DC bus, first of all, you have to first of all feed an AC load. Now, since this is our DC bus, you have to convert first of all DC into AC. That is done by this PWM DC to AC inverter. Now, this DC to AC converter or inverter converts DC into AC, and all types of AC loads are fed from this. Now, in addition to this, what we have two back-to-back connected converters. So this is one converter, this is another converter. They are interfaced or connected together with the help of a high frequency isolation transformer. Mind it, it's a high frequency isolation transformer. This transformer may be operated at a frequency of the order of kilohertz, not hertz. Okay. Now, this is one converter, this is another converter. So this forms our isolated DC to DC bidirectional converter, or what we very popularly call it as dual active bridge DC to DC converter. What is the job of this, or what is the function of this dual active bridge DC to DC converter? So it is a bidirectional DC to DC converter. Power can flow from this converter to this converter, or it can flow in the reverse direction. Under normal situation or under normal circumstances, when there is surplus power available on this bus, so when solar system or wind system is having full generation and we have surplus amount of energy available here, all types of AC loads are fed from here. And maybe there are some DC loads also which I have not shown here. So these loads, they get all the power from this bus. What happens if during any time of the day the generation from this site falls? Okay, so this generation can fall.
The sound is a bit lower. Sir, please enhance, sir.
Okay. Hello.
Yes, sound is a bit
Hello.
lower, sir.
Yes, sir.
Hello.
Okay.
Sir,
Wait
sound is a bit.
for a moment. Please bear with me just for a minute.
Yes, sir, now it's better. It's
Yes,
okay,
sir.
sir.
Yes,
Please
sir.
continue.
Yes. Okay. Okay. Sir, continue, sir. It's better sound.
Sir, please unmute your mic.
Am I audible now?
Yes, sir. You're audible.
Yes, sir. Yes, sir.
I can start from where I have left. This is our source of renewable power generation. Then we have a DC to DC boost converter. It increases the voltage level and it forms the high voltage DC bus. And from this high voltage DC bus, we can feed all types of AC loads through this inverter, PWM voltage source inverter. And then on the other side, we have another bus. It's a low voltage DC bus, which charges or which stores the surplus energy in energy storage system, which may be a battery energy storage system, or it may be a supercapacitor, etc. I have shown here only battery, but it could be supercapacitor also. Now, this is our isolated DC to DC converter. Okay, this isolated bidirectional DC to DC converter is also called dual active bridge DC to DC converter because it comprises of two bridges. This is one bridge, this is another bridge, and the two bridges are interfaced together with the help of this high frequency isolation transformer. The frequency at which this transformer operates is of the order of kilohertz. It may be 10 kilohertz, it may be 20 kilohertz, or so on. So therefore, the size of this transformer is pretty small. Now, under normal situation, when surplus amount of energy is available from renewables, okay, all these loads are fed from this bus, high voltage DC bus. And at that time, power flows from this converter to this converter. I mean, power flows from left to right, high voltage bus to low voltage bus, and then energy is getting stored in this battery energy storage system. Okay, let us suppose at any time of the day the generation from this side has reduced. Okay, we don't have surplus amount, or we don't have sufficient amount of power available here. So therefore, this low demand cannot be met from this high voltage DC bus. In this case, what will happen? Whatever energy is stored in this
Hello.
whatever energy is stored in this battery, what will happen? This
Hello.
battery will start now delivering power to this low voltage DC bus, and from this low voltage DC bus, power will flow from this converter to this converter, because I have already told you that it is a bidirectional DC to DC converter. Now power will flow now from low voltage DC bus to high voltage DC bus, and since this high voltage DC bus is feeding the load, so whatever demand is there for the load, that demand will be fed from this storage. So I repeat, for under normal situation, when there is surplus amount of energy available here, power will be the load demand will be fed by high voltage DC bus, and simultaneously power will flow from high voltage DC bus to low voltage DC bus, and the energy will be stored in the battery. And when the generation on this side reduces, okay, then power will flow in the reverse direction, because we already have energy stored in the battery, energy storage system. So power will flow from low voltage DC bus to high voltage DC bus, and the load demand can be met from here. So this is the role of bidirectional dual active bridge or bidirectional isolated DC to DC converter in a DC microgrid. It results in bidirectional flow of the power. Now this dual active bridge converter or isolated bidirectional DC to DC converter has applications, like it has one of the applications in electric vehicles. This is the schematic diagram of an electric vehicle. So in an electric vehicle, you have fuel cell stack, your high voltage battery, then you have this high voltage DC bus, and then on this side you have a low voltage DC bus. Now this high voltage DC bus feeds electrical motor, which is connected to the propulsion system, which results in the motion, in the rotation. And simultaneously here, what we do is that we use the same dual active bridge DC to DC converter. This is IBDC. IBDC means isolated bidirectional DC to DC converter, which is nothing but this. It is this converter, DC to DC converter. It's used in electric vehicles also here. What's its role? Its role is, again, it makes the power flow from high voltage DC bus to low voltage DC bus, where it is stored in low voltage battery energy system, and some low power DC loads are also fed from here. Okay, and then from this high voltage DC bus, we can see air conditioning system, power steering, etc. They are also fed. Now, this isolated bidirectional DC to DC converter or dual active bridge converter will result in reverse flow of power also. Whenever power is required from this low voltage battery system, it will flow in the reverse direction from low voltage DC bus to high voltage DC bus, where from it can be fed to various types of systems. It can be fed to DC to AC converter for electric motor. It can be fed to other accessories like air conditioning system, power steering system. This is one application of dual active bridge DC to DC converter. Another application is in modern uninterruptible power supplies, UPS. In case of UPS also, this is the mains. As usual, this is AC to DC converter. When we draw the schematic diagram of a UPS, generally in the class we are taught that this AC to DC converter is followed by a battery bank. It results in the charging of battery bank, and simultaneously it supplies power to the inverter. And this inverter, it is a PWM voltage source inverter. It converts DC into AC and feeds that AC to critical load. But in case of modern UPS, which use this dual active bridge DC to DC converter or isolated bidirectional DC to DC converter, what is done is that power comes from mains. Okay, it is converted into DC. So this is our high voltage DC bus, and then inverter converts this DC into AC and feeds the AC load. And simultaneously, what happens? This power flows in this direction. Whatever power is coming from mains, a part of that flows in this direction, and with the help of this bidirectional isolated DC to DC converter or DAB, the power is stored in the battery bank. You may have a 12-volt battery, you may have a 24-volt battery pack. It depends upon the rating of the inverter. Okay, and then when mains fails, I mean when there is failure of the mains, power will be supplied by this battery. Now, since this is a low voltage battery, this DAB will convert this low voltage into high voltage, and then this high voltage will be fed to the inverter for continuous supply to the load. This is how this IBDC or DAB converter finds its application in UPS. Now, but our main topic is application of this bidirectional DC to DC converter or dual active bridge converter in DC microgrid. Now, there are different types of control techniques which have been proposed or which have been reported in the literature for the control of this dual active bridge converter. The prominent among them are single phase shift or SPS control method, extended phase shift EPS control method, dual phase shift DPS control method, and triple phase shift, that is TPS control method. Okay, I'm again showing this is the complete circuit diagram of dual active bridge. See, this is the DC side, this is the bridge, and this is the inductor, this is the high frequency transformer, and this is the other bridge. These are two back-to-back connected bridges. They are interfaced or connected through this high frequency AC link or high frequency transformer. And then this is the other side of this, may be low voltage DC bus, and this may be high voltage DC bus. So power can flow from low voltage DC bus to high voltage DC bus, or as demanded or as required, it can flow in the reverse direction. That is from low voltage DC bus to high voltage DC bus. Now, these are some of the waveforms which give an understanding about the operation of a dual active bridge converter, how it works. Now, this is the transformer primary voltage, which is square wave. We don't use any PWM technique here. It is normal square wave operation. This is the transformer secondary voltage. Let me show the transformer again. This is the transformer primary voltage, VP. Transformer secondary voltage is here, somewhere here. This is the transformer secondary voltage. Now, we can see the secondary voltage is leading the primary voltage by certain phase angle. This phase angle may be 5 degrees or 10 degrees. It depends. And then this is the voltage across the inductor. Which inductor I'm talking about? I'm talking about this inductor. This inductor has this voltage. And then this is the inductor current. You can see inductor current is increasing and then decreasing, then again exponentially rising, falling, and so on. And then this is the transformer primary current, I in. This is the primary side current, I in, and this is the secondary side current, I out. This is the primary side current, I in. This is the secondary side current, I out. Now, it is this primary side current and secondary side current which will tell you whether power is flowing from high voltage bus to low voltage bus or vice versa. Okay, and let me tell you that this phase shift, since the secondary voltage is leading the primary voltage, in this case power will flow from high voltage, that DC bus, that is primary side, to low voltage DC bus, that is secondary side. These are some of the objectives of closed loop controller, and this is our closed loop controller. Okay, this is our solar PV, which is used in DC microgrid. And you have a DC to DC converter also here, boost converter, which I have not shown, and this is our high voltage DC bus here, and then this is our load. Okay, and this is the reference voltage. Let us suppose we want a voltage of 300 volts, and this is the actual voltage. The difference between the voltage is processed in a PI controller, and then this PI controller determines the phase. It gives the signal to phase modulator, and this phase modulator determines this angle, which I have already discussed with you. This angle, phase angle, is determined by this PI controller. It is by this phase modulator, depending upon the error. And then it operates the bidirectional converter, DAB, and accordingly, power can either flow from high voltage DC bus to low voltage DC bus or vice versa. And simultaneously, it will maintain the bus voltage constant. That is the purpose of this closed loop control. The main purpose is to maintain the DC bus voltage constant. These are some of the system parameters on which we have tried some of the simulations. The high voltage DC bus we have taken as 300 volts. The low voltage DC bus we have taken 50 volts. And this is the capacitance values on the input side and output side. This is the leakage inductance. This is the transformer ratio, 300:100, and we have taken a load resistance, and we have changed this load resistance from 10 ohms to 5 ohms. So we are perturbing the load to just test the controller, whether the controller is able to maintain the DC bus voltage constant or not. Okay, now you can see this SPS control. This is the load current. Up to 0.09 second, our load current has a magnitude of 5 amperes, and after 0.09, this current gets almost doubled. It reaches about 9 or 10 amperes. So with this perturbation in the voltage, the main aim of the controller is to maintain the bus voltage constant. And you can see with the even with the perturbation in the load current, the voltage does not change. It remains absolutely constant. These are the waveforms for power flow in forward power flow. Now forward power flow means power flow from this converter to this converter. That is high voltage DC bus to low voltage DC bus. You will be able to understand it with the help of these waveforms. As usual, this is the primary voltage, this is the secondary voltage, these are the inductor voltages and currents. Let us try to concentrate on these voltages, these currents, input current and output current. So let me again show you what is the input current. Input current is this current, that is current coming out of the source, and output current, I out, is the current going into this source, and it will be very much clear to you. Now, since this input current is negative, now this current will be negative only. It's showing input current negative. Now, what does negative current mean? Current means current is coming. It means that current is coming out of this. Okay, that is power is coming out of this, and simultaneously you can see output current is positive. Okay, what does positive current mean? You can see output current is positive means it is flowing in this particular direction. That means power is flowing from primary side to secondary side, or to be more specific, I would like to say power is flowing from high voltage DC bus to low voltage DC bus. How do we come to know about that? We come to know about that by the polarities of these, by the directions of these currents or polarities of these currents. This I in is taken negative in this direction and positive in this direction, and this I out is taken positive in this direction and negative in this direction. Now the graph shows that I in is negative and I out is positive. You can see graph is showing that I in is negative and I out is positive. That means power is flowing from high voltage DC bus to low voltage DC bus, and this phase shift also, it is in conformation with this phase shift, because this voltage leads this voltage, that is the transformer secondary voltage leads the primary voltage, and it makes the power to flow from high voltage bus to low voltage bus. This is reverse power flow mode. These are the simulation results that we have taken. Now in this reverse power flow mode, you can see now primary voltage is leading secondary voltage, whereas in the forward power flow mode, you can see secondary voltage is leading primary voltage by certain phase angle. However, in reverse power flow mode, primary voltage leads the secondary voltage, and since primary voltage leads the secondary voltage, the direction of power flow will be this. It will flow from this bus to this bus, and that we can verify with the help of these polarities of the currents. Now we can see I in is positive and I out is negative. Okay, in the previous case, I in was negative and I out was positive. In this case, I in is positive and I out is negative, which confirms that the power flow has changed its direction. Now it is flowing from low voltage bus to high voltage bus. This is how a DAB works. This is how we use it in a DC microgrid. Let me show you DC microgrid again. This is our DC microgrid. Whenever there is surplus amount of energy here, it the energy is supplied to the load through the inverter, and simultaneously through this DAB, power will flow from high voltage bus to low voltage bus, and that will result in the storage of the energy in the battery. And whenever there is deficiency of energy here or deficiency of power here, okay, the load demand is no doubt it is taken care of by this, but it is not able to take care of all load demand. The rest of the load has to be supplied by this battery storage system. In that case, whatever energy is stored in this battery. That energy has to be supplied to the load. That means power has to flow from low voltage bus to high voltage bus. And then when power comes at high voltage bus, it is then fed to the load. This is how a DAB does it. With the help of waveforms, I have shown you how we can make power to flow in the forward direction and how we can make power to flow in the reverse direction. Actually, it is not we who are doing this. It is the controller, a closed loop controller, which will do this. Okay, these are some parameters that we noted during taking these simulations, switch stresses, etc. And these are the system parameters for which we performed these simulations. And we have taken the solar, input power of solar PV constant here, but in other simulation we made it variable, and with varying solar insolation we have also taken simulation results, and we have seen how this DAB takes care of varying this generation from solar power, and how it supplies the load demand, keeps the load demand constantly supplies the load demand. I have not shown those results here, those simulation results here. However, you can see power characteristics of battery on low voltage side. These are the characteristics of battery on the low voltage side. Here, power power is negative. It means power is absorbed by the battery. Okay, and when power is positive, it means power is delivered by the battery. Okay, when power is delivered by the battery, it becomes positive, and when it absorbs, that stores the energy, it is negative. So these are some of the results that we have taken in our simulations. And this is again load perturbation. When we are changing the load, the bus voltage does not change. The closed loop feedback loop ensures that the load, this bus voltage, remains absolutely constant. I have then asked my research scholars to go for experimental validation of whatever simulation results they had generated. I have not showed you all the simulation results. I have just showed the part of it given the time constraints. This is the experimental RT lab verification of DAB as a power electronics interface for bidirectional power flow. This experimental setup was established in our power electronics lab in electrical engineering department. This is the 4-channel DSO which was used. This is the host PC, and we used Opal RT digital real-time simulator for our controller purposes. These are some of the features of Opal RT. I will not go into details. These are the experimental results that we captured with the help of this Tektronix digital storage oscilloscope. This is the primary voltage, it's written here, and this is the secondary voltage. In this case, you can see secondary voltage leads the primary voltage by certain phase angle, and this is the inductor current. This is inductor voltage, and this is again inductor current, and therefore power flows from high voltage bus to low voltage bus. In the other case, you can see the primary voltage is now leading the secondary voltage, and these are the inductor currents, and in this case direction of power flow will be reversed. That is, power will flow from low voltage bus to high voltage bus. And this is the output current. See, output current is at a particular value for a certain period of time, and then we perturb the output current. We change the load from some low value to high value to test our controller. You can see our controller, initially when the load increases, voltage momentarily dips, and then controller very quickly acts and it maintains the load voltage constant. It takes load voltage back to its normal value, bus voltage. Okay, these are the RT lab results again for application in DC microgrid. Now what we did, we created a sort of DC microgrid situation and took the experimental results again. Okay, this is for forward power flow, and this is for reverse power flow. Here you can see primary voltage leads the secondary voltage, and these are the inductor currents. And this is the battery voltage, and this is the battery current. And this is again output voltage, output current. Perturbing output current or load current does not change the load voltage. Load voltage remains, constant. Thank you. That's all. This explains the role of dual active bridge DC to DC converter, or what we call as isolated bidirectional DC to DC converter, how it affects the bidirectional bidirectional power flow from low voltage bus to high voltage bus, or from high voltage bus to low voltage bus, as per the demand, and its application in DC microgrid. Thank you.
हेलो, हाँ सर, कर दिया मैंने सर, वो फिर मतलब सही सर। सर वो नहीं सर, उसमें कमेटी में ये था कि सर कि वाइस चेयरमैन और एचओडी और कोई एक कोऑर्डिनेटर और कोई भी एक मेंबर हो सर, चल जाएगा।
Thank you, sir. Yes, any participant?
Hello. Yes, sir.
Hello.
Sir, I have a question. Like, how we'll manage with the voltage fluctuations when it will be when there will be load change or some sudden load change. So, how we'll be tackling that in this?
It will be tackled by the closed loop controller, voltage controller, PI controller. Where I have already shown you the closed loop controller, schematic diagram of the controller, and the main objective of the controller is to maintain this voltage constant, take care of these voltage perturbations.
Okay.
Any other query?
Yes.
I hope I.
Sir, good afternoon, sir.
Because the problem is that here I'm using 2G network. So was I audible?
Yes, sir, you are audible. No
Yes,
issue,
sir. Yes, sir.
Okay.
Sir, I have a small doubt, sir. Can I ask?
Yes, please.
Hello, sir.
Yes.
Sir, sir, how much cost to implement this in laboratory, sir, around, except computers and other things? To implement this
Can you please repeat
around
your voice is not clear. Can you repeat your question?
Yes, sir. Yes, sir. Yes, sir.
Yeah,
Sir,
please.
what is the cost to implement this in our laboratories?
See, if you are using, I got your question. We used Opal RT, digital real-time simulator, which is a costly item. Okay, so the other things will not cost much. If you have an inverter, you have bidirectional DC to DC converter, that will cost you a few thousand rupees. But it is the controller which may cost. However, if you can, avoid the use of costly equipments like Opal RT or DSpace, you can use a digital signal processor, DSP. A DSP may cost a few thousand rupees. The only thing, extra effort that you have to do in case of DSP is that you have to write the code. Generally, what students do, they are afraid of writing the code. That's why they go for shortcuts. They go for DSpace. They go for Opal RT. In case of Opal RT, you don't need any code writing of any code. So, but this solution becomes a very costly solution, because one Opal RT that we have purchased in our lab, it costs around rupees 33 lakhs. So, but you can do the same job if you are interested by learning the DSP coding. Yes?
Sir, how much?
What I was telling you? Opal RT is very costly. You can avoid the use of Opal RT. You can purchase a digital signal processor, which may cost you 10 to 15,000 rupees, and learn its coding, and then you can implement your controller through DSP. In that case, it will become a very cheap setup. Otherwise, if you go for Opal RT, it's a costly affair.
Sir, thank you, sir. Thank you very much, sir. Thank you very much.
Welcome.
Hello,
So
sir, I have a question.
Yes.
Hello.
Yes, please.
Sir, I am audible?
Yes, you are audible.
Sir, how to maintain the voltage stability in a DC microgrid?
See, voltage stability is not our area of interest. What we did, we used a DC dual active bridge DC to DC converter. Our research was mainly focused on the performance evaluation or performance investigation of this DAB converter and to maintain the bus voltage constant. Okay, stability was not our area of interest. That was not our area in which we did not work in that field.
Okay, sir.
That pertains to power systems. We are from power electronics, so our main focus was to improve the performance of dual active bridge converter. Stability was not our concern.
Okay, sir. Okay, sir. Thank you, sir.
So there's one more question.
Yes, please.
Now this question is from Mr. R.S. Kiran. So he's asking, now with the help of DAB, could EVs be produced easily? Electric vehicles, he's asking, I guess.
Yeah, yes, it's already there. The companies have already started using this DAB in the electric vehicles. Because in electric vehicles also, I have shown you in the schematic diagram, block diagram, that DAB is used and it results in the bidirectional power flow. The power flows from high voltage bus to low voltage bus, and there it is stored. And whenever you require that stored energy, the power flows in the reverse direction. It's already there in electric vehicles.
So there is one more question
Sir,
from
please
Mr. Rohit
provide
Arora. It's like he's asking, it's one of the way to address intermittency of renewable energy, microgrid integration, how effective it could be, and what are the major challenges to make it effective?
Yeah, actually the use of application of DAB is not very old. It is still in its infancy and it is on the research table. The researchers both in academia and industry are still working on it. It's a new topic. It's not a very old topic. It is still in its infancy. So many issues are there. Like, I have not touched all the issues because my presentation was very brief. I did not have much time. As you know, in these presentations, we cannot talk much about whole wide spectrum of the research. Choosing the duty ratio for control, for choosing the most optimization is another issue in which my research scholar worked, and he, out of many duty ratios, he had to choose the best optimum duty ratio at which the dual active bridge converter will give the most efficient operation. Okay, so it is still in its infancy. It is on research table. A lot work is still expected in this area.
So I can't see any more questions. Anyone else who wanna ask questions from sir? Shall we continue?
Sir, please provide your email ID.
You are addressing me?
Sir, please provide us email.
Yeah. You can note down my email ID is bh80. If you have pen and paper, you can note down bh80. D for department, E for electrical, E for engineering. bh80 DEE @nitsri.ac.in. But DEE @nitsri.ac.in.
Okay, sir. Okay, I got it. Thank you, sir. Thank you so much.
Okay, most welcome.
Sir, one more question I can see from Rohit Arora. Regenerative braking in electrical vehicles. Can it also be addressed by DAB converter?
Regenerative braking, yes, that can also be addressed using dual active bridge converter. Because for regenerative braking, the primary requirement is bidirectional power flow. And since a DAB is a bidirectional DC to DC converter, so it can address that issue also.
Okay, one more question from Akib. Sir, how does current converter allow reverse flow of current when PE switches are used at present?
Switches? When
PE power electronic switches are used at present?
Yeah, because see, in these converters we have IGBTs, and IGBTs have got anti-parallel connected diodes. Okay, so these are two quadrant switches. Two quadrant switches means the direction of current can reverse. Voltage will remain same, polarity of voltage will remain same, but the direction of current can very easily reverse in these two quadrant switches. In DAB, we are using two quadrant switches, IGBT switches. So the direction of current is not an issue. The direction of current can very easily reverse.
One question from Sonam Dholkar. Sir, how is the grid system for EV charging station?
How is that?
How is the grid system for EV charging station?
How is the grid system for
EV, electric vehicle charging station?
I didn't get the question. What she actually wants.
This question is incomplete.
I don't think so.
Can anybody complete this question?
Sonam, can you please unmute your mic and you can directly ask. Or we can
hello,
take
sir?
next question.
Yes.
Hello.
Yes.
Sir, is the grid system like DAB application is also used in electric vehicle charging stations?
No, right now it is not used there. It's not used for charging stations because you don't need bidirectional power flow there. Their power flow is in only one direction, because whenever you go for charging of your battery bank, the power has to flow
Then,
only
sir,
in one direction. I don't think it is required there.
okay, sir? Why is it challenging even now to establish those stations?
I think in near future, see, electric vehicle industry, if you see in India also, it has not yet taken up. With the passage of time, I think these electric charging stations will come up. It's a matter of time only. Maybe next 5 to 10 years it may take for complete commercialization, and these charging stations have to come. I don't have any idea about technical part of it, but in future maybe it may take next 5 to 10 years to come up.
One more question is there from RS Karan. Would there be any kind of fluctuations or vibrations due to DAB?
Fluctuations in what voltage?
I'm not sure. Karan, can
Fluctuations. Kiran can directly ask the question.
Yeah, voltage he's asking.
No, the controller always ensures that voltage is maintained absolutely constant. There will not be any fluctuations in the voltage. It depends upon how good your controller is. If you have designed a controller which is very well tuned, it will take care of all sorts of fluctuations.
So we may have wind-up issues, I guess, like whenever we are using DI controller. Maybe due to wind-up issues,
Yes.
the system may get relatively slow. Is it?
It depends upon how well tuned your system is. If the system is not properly tuned, then your settling time may go very high and system may become slow. It depends. Instead of using these PI control, see, it depends how well tuned your system is. You can go for fuzzy logic based controller, fuzzy logic based controller, ANN based controller, or if you are an expert of control systems, you can design your controller very well so that its settling time is small, it does not give rise to overshoots and undershoots, and it's very quick in response. It depends upon how well you design the controller.
Got it, sir. Thank you.
Thank you.
So I guess we are done with the questions. There is no more questions in the list in the chat. Thank you so much, sir. It was really wonderful. And as you are telling, your network is 2G, but still you have managed and you have given the presentation. So really thankful to you, sir. And I guess we'll be able to
Thank you so
get
much.
some help from this research.
Yeah. Thank you for giving me an opportunity to deliver a small talk on this topic. Thank you so much.
Participants' feedback form is already there, so we can fill that, and we'll be meeting tomorrow at 10.
Okay, thank you, sir. Thank you for sparing time for us. We'll definitely get back to you.
Can I leave?
Sorry? Sir, we will get back to you if required.
Can I leave now?
Yeah, yes, sir. Yes, sir. Please.
Okay, thank you so much. Thank you.
You're welcome, sir.